Hello everyone, my name is Dustin Overmiller, and for my project I did a parallel approach to solving the Sudoku puzzle. As a quick background of what a Sudoku puzzle is, it's an n by n grid that contains the numbers 1 through n, and the goal is to fill in all the missing numbers in the puzzle. To do this you have to apply the rules, which are that each row, column, and subgrid, which are outlined in the dark black lines, must contain all 1 through n numbers. And now from these rules we can imply that no row, column, or subgrid can contain duplicate numbers, and we use this as a validation technique. As for the importance of the study, there are millions of people that already play the game, and to have a faster solution would be beneficial. What we'll find is that as the puzzle becomes harder or larger, the number of paths to search will grow exponentially, and we can see two examples of larger puzzles listed below. Furthermore, for this study we'll only be focusing on harder or larger puzzles. People can already easily solve the easier puzzles without a problem, and the sequential case can easily handle this in a fast time where we don't need a parallel solution. So like I said before, the number of paths will grow exponentially as it becomes harder or larger, so the time to wait for a solution could grow exponentially. A blank n by n grid has a total of n raised to the n times n paths. So if you're increasing your grid size, which would increase n, or if you're removing the entries from the list and you're getting closer to a blank grid, your growth rate would be exponential. And an example of the second case is listed below, where you have one search tree, but if we remove an entry from that puzzle, you could get a search tree such as the one on the right, which is an exponential increase. Now the general idea to solving the puzzle in the sequential case would be to create a possibility list for each of the blank entries, and we try to apply the rules to remove possibilities until we can fill in each of the blank entries. So as an example, in the top right we see that the top two rows have the number 5 going across, and in the far right column we have a 5, so the only possible location for a 5 in the top right subgrid is the bottom left location. Now we continue to apply these rules until we can no longer do so, and we make a guess. After we fill in our guess, we again try to apply the rules until we find a solution. So for the sequential case, you'll have your search tree, and it'll search one path at a time from left to right. It'll go down path 1. If it's not a valid solution, it'll backtrack and go to path 2, and it'll continue until it finds a solution, then it returns the solution. If it searches all paths and no solution is found, it'll return saying that this was the case. Going into more detail about the reduction technique, it will loop until a reduction cannot be applied. A reduction is either a blank entry gets its value filled in, or its possibility list is updated to remove a number. And we do this because this could have an effect on other blank locations. So for each blank entry in the list, we will grab in the associated row, column, and subgrid all of the numbers that are filled in. And by applying the rules, these numbers cannot be in that location, so we remove them from the possibility list. If there's only one possible number in the list, it's got to be there, so we fill it in. Otherwise, what we'll do is, for that entry, for each of its possible numbers in the possibility list, we'll see if this number exists in the associated row, column, and subgrid other blank entries. If the number does not exist in any of those possibility lists, then we also know that the number must exist in that location. So as an example of the second case, we saw that previously in the top right subgrid, where all of the blank entries except for one could not have 5 in its possibility list, so 5 was filled in the bottom left location. As for the first case, where a possibility list only has one entry, you can see that in the far right column, in the bottom right subgrid. All of the other numbers 1 through 9, except for 4, are already filled in somewhere in the row, column, or associated subgrid, and so 4 has to be the only possible number there, and it gets filled in. As for making a guess, as far as when it comes to making a guess, if we have to, we need to pick the best possibility, which would minimize the paths to search. So as an example, you have one blank entry with 5 possibilities, and one blank entry with 2. So the possibility of guessing the correct number for the first case is 1 over 5, or 20%. The possibility in the second case is 1 over 2, which is 50%. So we could see that we have a higher probability in the second case, and our best option would be to choose the possibility list with the fewest number of entries in it. And that pretty much takes care of the sequential program. As far as current parallel work that's been performed, there has been a paper by the authors listed where they compute a 16 by 16 Sudoku puzzle and perform a parallel program on that. In their parallel program, they push all temporary puzzles onto a stack, and then they pop a puzzle one at a time and try to solve it until they find a solution. In their approach, they used either locking or message passing techniques to obtain the parallel performance. Now, the issues I had with that approach was that it was not expandable. The paper clearly stated that the stack could not handle grids greater than size 16 by 16. And so that's a clear problem with people that would like a solution to much larger puzzles, because they do exist. Furthermore, the approach was not scalable. It reached a limit at about 4 threads. We can see in the graph that after about 4 threads, the execution time does not decrease. In fact, in the MPI case, in the blue line, it actually increases. So we need a better scalable approach. And the biggest issue with their approach was that the locking caused bottlenecking, and in the MPI case, the thread communication caused the threads to wait, which did not lead to independent work. So before I get into my parallel approach, some key puzzle observations that I made were that as the puzzle becomes harder, there are actually multiple solutions. There's not just one. So you have a higher probability of finding a solution faster by searching through multiple paths. And then on top of this, your sequential algorithm spends most of the time solving the puzzle and making guesses, because it's a harder puzzle. So this is very independent, and we could have each thread do this independently without having to worry about much overhead with thread communication. And we could see a gprof picture demonstrating this, where it spent most of its time in the reduction and guessing state, which is the apply reduction function. So for the parallel approach, the general idea is that we will take the sequential method and we'll give each thread a puzzle to solve, so we're searching through multiple paths at once. Now, because there are so many for loops, the best approach was to use OpenMP, and I stayed away from MPI because of the message passing having an issue as threads were increased. So like I said, we use the sequential method approach, and the first thing we have to do is to apply a reduction to get the best location for a guess. So what we'll do is we will make a guess, or we'll apply a reduction, get the best location for a guess, and give these puzzles to the different threads to solve so that we have multiple paths. Now the overhead for this initial sequential search or reduction state is very minimal, because it's such a hard puzzle that it won't spend a whole lot of time in there reducing, and we will get to the first guess very quickly, so the overhead for this is minimal. And like I said, so we'll spawn a thread for each puzzle to solve. If there are more threads than puzzles, they'll be put on a queue and wait for work to be given to it. So the work would be given to it at the time that a thread working makes a guess. When it comes to making a guess, the thread will look to see if there are any threads waiting, and if there are, it will give them a puzzle under one condition. Otherwise, it will continue itself to try and solve the puzzle. Now that condition would be a threshold. What we want to do is we want to make sure that the overhead for waking up a thread and giving them the work does not exceed the amount of work left. So if we're very low in the search tree, the time to perform the wake up would be much greater than the time it would take for the thread to actually perform the work. So what I have in there is a threshold, and you can see in the diagram on the right, after a certain point the thread will just continue work itself without waking up any other threads, and this provided the maximum or optimum approach. So here we can see some timing results. In the sake of time, I won't go into too much detail here, but generally what we could see is that in the 9x9 case, the sequential program was already optimal and we didn't need a parallel solution. Now as for the larger cases, like in this one we have a 16 by 16 case, the efficiency and speed up was actually increased in the medium difficulty, and then the hard difficulty it actually took a very long time because of the exponential growth for the sequential case to find a solution, while the threads actually found a solution very quickly and I was able to obtain very efficient performance. Now as a note, all of these tests were performed over 5 puzzles and an average was taken, so that it wasn't just one case because all puzzles are different. Now lastly, I did a 25 by 25 case, and this was done on a very easy puzzle because it was taking way too long for the sequential case to solve it. It was somewhat on the order of hours, and I never gave it enough time. It probably would take a day or so for any more difficult puzzle to be solved. So because of that, I had to use a very easy puzzle just to demonstrate that the algorithm will work on larger puzzles other than the 16 by 16 case. But I couldn't get very great performance because of the fact that it was a very easy puzzle. However, because of the exponential growth of the problem, going to a medium puzzle would give very significant results. And we can see in the timing in the different graphs the following. We can see that in the 9 by 9 case our timing is already very low, so parallel performance doesn't increase that. But we do start to see the performance take effect in the 16 by 16 medium case, and here in the 16 by 16 hard case we see a significant effect in that it goes from a very long time to a very short time very quickly. And this leads to a very significant speed up performance for the 16 by 16 case rather than the 9 by 9 case. But like I said, the sequential program operates just fine, so we wouldn't need it for that case. So here we can see very significant results in speed up, and a speed up factor greater than the number of threads, significantly greater, for the 16 by 16 hard case. And also the efficiency shows that, where we have significant decrease in the 9 by 9 case, but we get almost optimal performance in the 16 by 16 medium, and above optimum performance in the 16 by 16 hard case. And so, in conclusion, we see that the sequential solution works fine for the 9 by 9 or easy puzzles. There's not enough paths or work for the threads to keep busy. And in more detail, I was able to obtain much better performance than the previous work that was documented in the paper. My thread work was much more independent, and I also used the statistical property of the multipath search, in that I would be able to find one of the multiple solutions faster by searching through multiple paths rather than trying to optimize a single path. This led to more independent work and much greater results. So in detail, in conclusion, I was able to have a program that was much more expandable, and even though in the easy case it didn't provide any significant improvement, which I wasn't surprised about, I was able to expand to a case larger than 16 by 16, and I was able to provide much more significant thread scalability, in the sense that I wasn't limited to just 4 threads. I was still getting optimum performance even up to 16 and greater than that. And these are the references that I used for my research. If you have any questions, please let me know in the discussion. Thank you.